Hello, 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 and welcome to this video on gas laws. In this video, we are going to be discussing the combined gas law. So the combined gas law states the relationship amongst pressure, volume, temperature, and number of moles of a gas under two sets of conditions. So if you look at the equation for the combined gas law, you'll notice it probably looks fairly familiar. All the different independent individual gas laws that we have learned about thus far are more or less included in this. You've got Boyle's law here, P1 V1 equals P2 V2. You've got Avogadro's law here. You've got volume temperature, Charles's law, and you've also got Gay-Lussac's law, pressure and temperature right here. And so what the combined gas law is doing is you're saying you have a starting pressure, volume, number of moles, and temperature, and you change them. So your pressure, volume, temperature, what is the new number of moles? What is the new volume? What is the new pressure? What is the new temperature? Keep in mind, when we're using the combined gas law, you must use Kelvin for temperature. So if you're given your temperature in Celsius, you're going to need to convert it to Kelvin using significant digits before you continue with your calculations. So where did we get the combined gas law? It's actually derived from PV equals nRT, which this is called the ideal gas law. We're going to use learn about this law in a later video. But what the ideal gas law does is it relates pressure, volume, number of moles, and temperature to a value called R, which is a constant. And R will always equal PV over NT if you rearrange that equation. So if we have, remember, a change, we change something, and we have two sets of conditions here, then R is going to be equal to the PV over NT for the first condition, and it's also going to be equal to the PV over NT for the second condition. Therefore, these two are going to be equal to each other. It's important to note that typically when we use the combined gas law, we are not going to use N1. Normally that's going to be more or less non-existent because we're using the same amount of gas. We're simply going to be changing the pressure, the volume, and the temperature. So remember, we're typically going to use the combined gas law when we have two sets of conditions surrounding one gas. But what do you do if one of the factors is not mentioned in a question or is held constant? In that case, you would simply take that variable that you're looking at in this combined gas law and you would get rid of it. So for example, if your temperature was held constant or your temperature simply wasn't mentioned in your problem and all you were dealing with was pressure and volume, you wouldn't worry about temperature. And the same would be true if you were not worrying about volume or not worrying about pressure. You would just eliminate it from the equation and solve with the variables that you are dealing with. And remember, when you're talking about temperature, plugging it in or solving, you have to use Kelvin. So let's go ahead and solve an example problem here. And I've got a chart on here to plug my variables in that you can use or not use depending on your style for solving these problems. So it says a gas at 155.0 kilopascals and 25 degrees Celsius occupies a container with an initial volume of 1 liter. By changing the volume, the pressure of the gas increases to 605 kilopascals as the temperature is raised to 126 Celsius. What is the new volume? So when I'm doing this, I'm going to be looking for my new volume, which is V2. And remember, we've got one gas here and two sets of conditions. So I've got an initial condition and a final condition. So my initial pressure is 155.0 kilopascals. My final pressure is 605.0 kilopascals. My initial volume was 1.00 liters. My new volume, we don't know, so I'm going to leave that as the variable V2. My initial temperature is 25.00 degrees Celsius. So to that, I have to add 273.15. When I do that, I get 262.15. And my new temperature is 125.0. And again, I have to add 273.15 to that, and I get 362.15. So now I'm going to go ahead and plug and chug. So I've got P1 V1 over T1 equals P2 V2 over T2. Plug in my variables. Plug in my volume. My initial temperature, 262.15. My pressure, 605.0. And note that I left V2 as a variable. I'm going to solve for V2 by doing cross multiplication. So the way I would do that, if you're not really sure of the algebra, you multiply and then multiply everything here, and then divide to solve for V2. And so I get V2 as being equal to 0.3593, but I have to take it to 3 significant digits, and so it's going to be 0.354 liters, and that is my new volume of this container. Let's do another example. In this one, we have an initial temperature of a 1 liter sample is 20 degrees Celsius. The pressure is decreased from 720 millimeters of mercury to 360 millimeters of mercury, and the volume is increased by 2.14 liters. What is the final temperature? So in this case, we're going to be solving for something underneath our combined gas law in the denominator. So again, I'm going to fill out my chart down here. My initial pressure is 720, and it's going to decrease to 360. My initial volume is 1.00. My new volume is increased by 2.14, which makes my new volume 3.4. My initial temperature was 20 degrees Celsius. When you add 273.15 to that, you get 293.15. And my new temperature is what we're solving for. So I'm going to go ahead and plug that into my equation. And now I'm going to solve for T2, which is down here at the bottom. Use the same mathematical method as we've used before. You're still going to cross multiply. So I'll show you. I'll cross multiply this, and you're going to set it equal to this. If you do it in multiple steps, you time both sides by T2, and then times both sides by 293.15 and solve. So I get my T2 in this case is equal to, it has to be 2 significant digits because my pressure is in 2 sig figs. So I get 460.246, which makes it 460. Remember, that's in Kelvin. So in order to put that back into Celsius, that's what I was given my initial temperature in, I'm going to subtract 273.15, and I get 187 degrees Celsius. And that's my final answer. Make sure you've taken good notes and come to class with questions. Thank you.